I want to describe some of the key points in figure 12.5. It's a complicated diagram, including data from summer and winter in the Antarctic of temperature measurements measured in air, soils, a freshwater pool, and the sea at 20 meters depth. It's the Antarctic, so remember the December data, which is in blue, is the summer, and the July data, which is in red, is winter temperatures. The first thing to notice in the left-hand panel is that the air temperatures in the summer they vary around about zero, with only a few temperatures going down to -8 degrees. It's a rather narrow range of temperature at this particular site in the summer, whereas in the winter at this site there's huge fluctuations of temperature from just below zero down to about -40. And the gradients of those fluctuations in winter are really very steep, um, and fluctuations can happen over a short period of time. If we look at the effect of those air temperatures on the soils, it's interesting to note that although the soils get very cold, um, around about -20, the fluctuations in the air temperatures are not reflected in those soil temperature changes. And that's largely because there will be a buffering layer of snow on top of those soils um, that will be helping prevent temperature change, and also the buffering capacity of the mass of soil as well. If you look at the soil summer temperatures, you'll notice that they're hugely fluctuating very much more than the air temperatures, and you'll also notice that they're elevated above the air temperatures, and that's of course because soil is dark and will be absorbing heat from the atmosphere and containing that within it. The fluctuations are so great, or the frequency of the fluctuations is so great, of course, because there won't be that snow layer on top that will be buffering the temperature change within the soils. The same can be true of the freshwater pool in the summer as well. You can see that the temperatures are elevated above the air temperatures, and you can see that there's huge fluctuations within the freshwater pool during the summer measuring period. And you can see that the pool is acting as a dark body as well and is absorbing heat, and therefore the freshwater pool temperatures are higher than the air. You'll notice that in the winter the red line is cooled down, as you would expect, but the air temperature fluctuations are not reflected in the freshwater pool, and that's because the freshwater pool has a large body and is buffering against this high frequency of temperature fluctuation in the winter months, and that's also because, of course, the pool will be covered in ice, and there will be snow on top of the ice, and that's affecting the heat exchange between the freshwater pool and the atmosphere. Is effectively forming a barrier, and depending on the amount of snow that's on top of the ice, that barrier or the buffering capacity of that barrier will be greater as well. The same is true of the sea as well. You'll see that the temperature in the winter um, gets down to about -2 when the temperatures of the air are -20, and that's because of the huge buffering capacity of the sea. It takes an awful lot of heat exchange to reduce the temperature down. The sea will be covered with sea ice, and on top of the sea ice, there may or there may not be snow that acts as a very good barrier um, to to heat exchange as well. So you'll notice that within the sea, there are, despite the huge changes in temperature in the air, there's very little change in the water temperature at 20 meters. Um, it gets down to about the freezing point of seawater in a fully mixed layer in the sea at 20 meters.